Hello and welcome to this video. In this video we're going to look in the practical of the experimental gas laws. Now the whole purpose of this practical is to try and prove that these things are true in experiment. This is why they're called the experimental gas laws, because they always hold true. And so basically we're going to design experiments in order to prove that these are true. We first have to then see or remember what are the experimental gas laws. Now we can only actually design experiments in order to investigate two of the three experimental gas laws, and the ones we are going to look at are Boyle's law and Charles's law. Okay, now Boyle's law is where we had the constant temperature. So we have constant temperature and we say that the pressure is inversely proportional to the volume, and Charles's law is where we have a constant pressure and we say that volume is proportional to temperature. If you're unfamiliar with these, I would obviously suggest go back to thermal physics and watch those videos before coming to watch this one. So let's first look at Boyle's law and see how we would devise this practical. So Boyle's law, our whole goal here is we are trying to prove that pressure is inversely proportional to volume. So this means we have to vary one of them and measure the other one. Now of the two of these, it's way easier to measure volume than it is to measure pressure. So what we're going to do is we are going to vary the pressure while measuring the volume. Now, in order to vary pressure, we still need to do it at a constant temperature. So we can't heat this thing up. What we can do though is say that pressure is going to be force over area. We know that we can, if we have a container and we don't change the shape of the container, then the cross-sectional area A will be the same for all of these measurements. So it means we just need to try and figure out some way that we can apply a force on the boundaries of this container so that we increase the pressure of the container. Now the way we're going to do that is we have a clamp stand and we need a container that has volume measurements, and the easiest thing to go with would be a syringe. Okay, so we have a syringe that is closed on one side because it needs to be a closed system, and on the other side we have a that plunger, and this is then the syringe, okay, where this is initially going to read an initial volume. So the first thing we need to do is read the initial volume, which we're going to call V0. Okay, so that's just the initial volume of this. Now, if I want to put a force on this, my force is going to be on the plunger, because I know that's the thing that I can physically move by applying a force to it. And so what I'm going to do is I'm just going to wrap a piece of string around here, and I'm just going to hook on some masses. And that mass is then going to bring a weight force, and that weight force is going to pull the plunger down, and that force divided by the area is going to change the pressure of this system. Now, the mass we can know pretty easily by using standard masses that will have the mass written on the side, so we don't have to measure the mass or anything like that. But if we want to get from mass to a pressure, we do have to know what the cross-sectional area of the inside of this syringe is, because that's the area that we're applying this force. Now the way we can measure the area, which we'll do over here, is we need to pull that plunger out of the syringe, which is possible. You just have to put a little bit of force into it, and you pull the plunger out and you will see that it will be something that looks a little bit like this. And then what we need to do is measure the diameter across here. Now to do that, we're going to use a vernier caliper to measure the diameter. And once we have the diameter, then we can then calculate the area, because we know it's circular, so that means the area is going to be pi times d squared over 4. Okay, and the force isn't going to be mass. The force is actually going to be mg, because it's the weight force, divided then by pi d squared over 4. Okay, and that's how we're going to convert from this mass to this pressure. Now, it's important to know that not only do we have an initial volume, we also have an initial pressure, because initially, before we change anything, the pressure is atmospheric pressure, right? So we have initially pressure is 1 atmosphere. Now we're going to read this in pascals, right, or newtons per meter squared. So that is 101,000 pascals. Now, if we are then going to see a change in volume, if we're applying a force so that we're actually pulling the plunger out, because that's the direction we're pulling the force in, that is then going to lead a decrease in the pressure inside the syringe, right? So that means that when I'm measuring these volumes, I'm always going to have an offset of V0. When I'm measuring these pressures, I'm always going to have an offset of the atmospheric pressure. That means that I need to correct all of my readings of the pressure and the volume. So I'm going to correct this by saying that actually delta V, so this delta V is going to be my change in volume, so this is the actual thing that I'm going to plot on the graph at the end, is going to be the volume that I read minus the initial volume, okay? Because I know that by doing this, my delta V is going to increase, which is expected, okay? Now, I am then going to say, if I am going to cause a decrease in the pressure, I want my pressure to still be a positive value. So I'm just going to rearrange the equation where it should be the final minus the initial. I'm now going to make it the 101,000 minus whatever pressure we calculate from this formula over here. And these are the two measurements that we're going to make. So I'm then going to vary the different masses. So I'm going to vary M, and that must be for at least 6 different readings. And that is then going to leave me with a table that I can plot, where I'm going to have all the different values of M in kilograms. I'm then going to have all the different values of V in whatever units the syringe is in. I'm going to use in milliliters. It does not matter what units you're in, because the proportionality will be the same for any unit system. And then I have to make sure that I am converting to everything. So I first need to convert from the mass to the pressure using the formula up here. And pressure, we measure it in pascals. And then I need to correct all of these measurements. So I then need to find what delta P is, still measured in pascals. And I need to find what delta V is, still measured in milliliters. And then I'm trying to prove the proportionality that P is inversely proportional to V. So what I'm going to plot on my axis is going to be P on this side against 1 over V, and technically I'd be plotting delta P and delta V. And you should end up with a straight line passing through the origin, and then you would conclude that since the graph is a straight line, you then end up with the proportionality that delta P is inversely proportional to delta V, or pressure is inversely proportional to volume, and hence it works. Now we then move on to Charles's law. Now Charles's law is a little bit trickier than this, but not too much. So Charles's law is we need to try to maintain a constant pressure, which means that we need to basically allow the system to come to its own pressure. That pressure will be the equilibrium pressure, and it will always be the same if we leave it for enough time. In order to do this, we need to be able to vary. So basically what we're saying is we're trying to show that the volume is proportional to temperature, which means, again, we have to see which one is easiest to vary and which one is easiest to measure. In this case, they're both pretty easy, but the way we're going to design this experiment is such that we are going to change the temperature and measure the volume. Okay, so we are going to vary the temperature and measure the volume, okay? And the way we're going to do this is quite a clever setup. We're not going to have a syringe or anything like that. Instead, we're going to have something called a capillary tube. Now, a capillary tube is a very, very thin glass tube with one sealed end, and our purpose here is we want to seal some gas into this tube. Now, the way we do that is we put in a small amount of liquid such that it will fall down the tube until it reaches some sort of stable position. Now, the liquid that we're going to use in this case is a drop of sulfuric acid. Okay, so a drop of sulfuric acid. This then represents a hazard, right? Because these capillary tubes are very thin and they're very fragile. If you smash one of these or you drop one of these, it will get a drop of sulfuric acid somewhere. You don't know the concentration of this sulfuric acid, could potentially be dangerous. Okay, so moral of the story, don't drop the capillary tube. Then at this point, a fair question would be, how exactly are we going to measure the volume of gas that's sealed here without having a capillary tube with gratings on the side? Now, the way we can do that is to say that we're just going to say we know this is a cylinder, right? So you'll be able to tell that the test tube is circular. You're then going to be able to basically say, because it's circular the whole way through, it's a prism. So the volume that we measure is going to be the volume of a cylinder. Now you can calculate pretty easily the volume of a cylinder using pi r squared h, using GCSE maths. And we know that the radius is going to be the same no matter what, right? Doesn't matter what temperature we change it by, unless we melt the glass, we're not going to change the radius of the circle, which means that if we just measure the height, that will be proportional to the volume, and it will still mean that we can prove this relationship. We can also, if necessary, so if you are required to, you can measure the radius of this using a vernier caliper or a micrometer. So using a vernier caliper or a micrometer, you could potentially measure the diameter and then calculate the radius. However, I don't think personally that this would be necessary, because you're just trying to prove a proportionality. If you plot h against t, you'll still end up with the same proportionality as v against t, because h is also proportional to v. Now we need to figure out a way that we are going to measure the height, and the way we do that is we're just going to attach a ruler to this. Now my diagram of this is not going to be as accurate as the way you want to do it. You want to literally secure this capillary tube to a ruler as quickly as securely as you can, so that you can measure an initial height, which I'm going to call h0. So measure the initial height, which is h0. Then from there we have our setup, which means we know we have our initial volume of gas, which we're now just going to measure the height for, and we can now say that we need to start varying the temperature of this. And the also a key point that we should mention is this is still under constant pressure, because we have this open top on the capillary tube, which allows the air to move in and out, which means that we'll always have atmospheric pressure pushing down on this, and so we'll always end up with a constant pressure. Now, in order to vary the temperature, we are then going to put this inside a water bath. Now, a water bath is just going to consist of some sort of beaker filled with water. Okay, and we're just going to put that in. We obviously need to keep track of what the temperature actually is at each of these points, so we're also going to put a thermometer in here. And the thermometer is then going to play the role of measuring the temperature. Now, there is a little bit of a trick to this, which is that we're making the assumption that the gas in this capillary tube is the exact same temperature as the water that we're measuring. Obviously, there will be a slight difference when you initially start measuring it because you need the time for it to reach thermal equilibrium. But if you put the capillary tube in, you wait a few seconds, because this volume is very small, because it's a very thin gas, the reason we use a capillary tube is so that that time that we take for it to actually reach a thermal equilibrium is basically negligible. So you can make this estimate that the water will be at the same temperature as the gas. If you had a really thick capillary tube, so you had a very large area, the time it would take for the heat to then reach the center of that tube and then it would fully flush out to be the same temperature everywhere would be a lot longer, and then you'd kind of have ruined your results for your experiment. So what we are going to say then is we initially want this water to be hot. Okay, so we're going to heat up the water in a kettle. And then we're going to place everything in here. So we want it to start off hot. And then as the temperature starts to decrease, we'll, over regular time intervals, measure the temperature that we read on the thermometer and the height we read on the ruler. Now you have to be consistent with your height readings on the ruler such that you always have the height from the position on the liquid that you choose. In the diagram that I've specified here, you can see H0 starts from the bottom of the liquid, so all of your volume readings have to be from the bottom of the liquid. Okay, if they were from the top of the liquid, which they probably shouldn't be, they should probably always go from the bottom, but if you choose your initial measurement to be from the top, make sure all of your measurements are from the top. Okay, it doesn't really matter too much where you start from. It will just give you some initial y-intercept offset. But yeah, so what we're going to do is we are going to measure the height and temperature over 6 intervals, regular intervals, and then we can make a table of this, and our table is going to consist of the height in centimeters. It's going to then have the temperature in degrees Celsius. It will then have, if you so wished, at this point you could just do this and plot these two columns and then you'd be fine. If you are asked to by the supervisor or whoever is doing your experiment, and you follow this extra step here where you can calculate the cross-sectional area, you can then convert it into volume, which will be in centimeters cubed. And then that would conclude your table. This is basically everything that you need to know. And then you will plot either H against T or V against T. Now it doesn't really matter which way you do it. I'm going to plot H against T because I feel like that would be easier. So I'm going to say, because I am varying temperature, that's going to be along the bottom, and I am measuring the volume, or in this case I'm measuring the height, so H is going to be on the top. Now I am going to get a straight line graph like this, but you will find that it will not go through 0, 0, okay, or it shouldn't go through 0, 0. Now the only reason is, well, there's several reasons that you could explain this. The first being that we didn't take into account this H0 offset. The second being that this is in degrees Celsius. But again, we aren't trying to prove a full equation. We're just trying to prove a proportionality. So as long as we see that we have a constant gradient here, we can conclude that V is in fact proportional to T, and hence you have completed these two practicals. So hopefully none of this is too complicated. Obviously in your lab you'll get a rundown of what you should be doing anyway, and thank you for watching.